Hi, welcome back to section 10.3. Now we just got done talking about how to find the probability of an event that has replacement or independent events. Let's look at one where we have without replacement. Okay, what this means is if I have the word school and the very first time I draw the letter S, I'm not going to put it back, I'm going to throw it away. So that means the second time that I draw out of the bag, there will be no S in there. There'll be a C, an H, an O, an O, and an L, but no S. So what these are called is when we don't replace it, this is a dependent event. And we can use an area model to represent this. We just got to do something to the area model before we do any figuring. Okay, so let's do this same thing. Two letters are drawn at random from the word school. If they are drawn one at a time without replacement, what is the probability that they are the same letter? Write a teacher solution. Okay, so let's make this, once again, our first draw. And so we're going to draw a S, or we could draw a C, could draw an H, could draw an O, or an L. And our second draw, we could also draw an S, a C, an H, an O, or an L. Draw our area model. We're going to draw all of our possibilities, just like we did before, so everything is staying the same. Okay, so we could draw an S and an S, S and a C, S and an H, S and an O, S and an O, S and an L, a C and an S, a C and a C, C and an H, a C and an O, C and an O, C and an L, HS, HC, HH, HO, HO, HL, OS, OC, OH, OO, OO, OL, OS, OC, OH, OO, OO, OL, LS, LC, LH, LO, LO, and LL. Okay, now what I want to do here quick is I want you to recognize that this first O is going to be independent of the second O. So when I draw this one, my first O, those two will line up, and then we'll have this one and a red one. Here we'll have a red and a blue, a red and a red. So I separated those O's by color. I should have done that the first time. Okay, so now what we have to do is we have to recognize something. If I take an S out on the very first draw, can I draw an S the second time? No. So what I'm going to do is I have to cross off that possibility because it does not exist. You can't draw something that's not there. Okay, so let's assume that I took a C out the first time. I can't draw it a second time. I'm going to cross off that possibility because it can't exist. Same with the H. Now, if I look at the O's, if I draw out a blue O, I cannot draw a blue O again. It's gone. I can still draw the red O, but not the blue one. Now, if I draw the red O, I can't draw the red O again. I could draw the blue one, but not the red one. And if I draw an L, I can't draw an L. So basically what we're doing is we're taking out what cannot happen. And so the probability of the same is going to be equal to basically I have to look at everything that has the same letters in it. And there's only 2 of them. But now I have to count out all the possibilities. There's not 36 possibilities because we eliminated 1, 2, 3, 4, 5, 6. We eliminated 6 of them. So now there's only 30 possibilities, which is equal to 1 over 15. So the probability of getting the same letter is 1 over 15. All right, so now let's look at it with using an algebra model. Okay, so keep in mind here we have our school. So we want the probability of the same. So that means we need the probability of getting an S and an S plus the probability of getting a C and a C plus the probability of getting an H and an H plus the probability of getting an O and an O plus the probability of getting an L and an L. All right, so probability of getting an S the very first time is 1 out of 6. But the second time, we're crossing off the S, and there's no S's left, so that's 0 out of 5. Okay, so let's erase that part. Oops. Go back. So that's for the S and the S. Now let's look at the C's. Okay, the first time it's 1 out of 6, but it disappears. So we're going to multiply it. Sorry. Multiply it by 0 out of 5. Okay, what about the H's? 1 out of 6 times 0 out of 5. Now the O's. Okay, the probability of the O's is going to be 2 out of 6, but now I'm taking one of those O's out, so that means that there's only 1 O left, and there's only 5 things left. So it's 1 out of 5, because basically I took a O out. Okay. All right, probability of the L's is going to be 1 out of 6 times 0 out of 5, because we took an L out. All right, 0 times anything is 0. This is 0. This is 0. Multiply across, and this is 2 out of 30. And this is 0. 2 out of 30 reduces down to 1 over 15. And that is your answer. Okay, so that's how you do independent and dependent events, by drawing an area model and by doing algebra. Okay, let's look at some other ways of organizing data. Another way we can organize data is using a tree diagram. And usually we use a tree diagram if we are talking about 3 or more events. You could do it for 2 events, that's fine, but 3 or more is usually when we do it. So here's my example. We have a fair coin and it's tossed 3 times. What is the probability of getting a heads and 2 tails? Okay, so if I have a fair coin, here's my first time that I draw it. And I'm going to say, hey, here's my second time. And we're going to draw it 3 times. All right. So the first time I could draw heads or I could draw tails. All right, I'm going to set that coin aside. Suppose I took that first coin, I drew a heads and I set it off to the side. Now I'm going to take my second coin and I'm going to draw it. I could draw an heads or I could draw a tails. Works the same way. It doesn't matter what happened that first time. What happens is what's happening the second time. Okay, so now I do this again. Now I got this third coin. I'm going to set the first 2 aside and I could draw a heads or I could draw a tails. And I could do the same thing all the way through. So basically what I'm doing is I'm just branching off of each of my events. Okay, so now all I have to do is read this. So let's read this. I could get a heads the first time, a heads the second time, a heads the third time. So I could get a heads, heads, heads. Or I could get a heads the first time, a heads the second time, and a heads the third time. Heads, heads, tails. Okay. Or I could go heads, tails, heads. Heads, tails, heads. Or I could go heads, tails, tails. Heads, tails, tails. Okay, so I come down here and I could do the same thing. I could do tails, heads, heads. Or I could do tails, heads, tails. I could do tails, tails, heads. Or I could do tails, tails, tails. So what I did is this represents all the possibilities. All the possibilities right there. Okay. So the question is, what is the probability of getting heads and 2 tails? It doesn't matter. It doesn't have to be in any order. I just want a heads and 2 tails. So I see right here that I have heads and 2 tails there. I have a heads and 2 tails here. And I have a heads and 2 tails here. So the probability is what I want, which is 3 of them out of 1, 2, 3, 4, 5, 6, 7, 8. And the answer is 3/8. Okay. All right, let's see what else we have. 2 more examples. So this time we have a pie chart. So a spinner has a 36-degree red sector and a 45-degree blue sector. The rest of the spinner is green. What is the probability of attaining each color? So first of all, this is talking about degrees. Let's figure out the green one. Let's figure out how many degrees that is. There's 360 total degrees, and we're going to minus the 36 plus the 45. So if I subtract that, I should get 279 degrees. So the green is 279 degrees. So we're going to put 279 degrees here. Okay, so the probability of spinning a red, then I want the probability of spinning a blue, then I want the probability of spinning a green. It's what you want over the total amount. So for a red, I have 36 degrees. Total degrees is 360. And when I reduce that, that's 1/10. The blue is 45 degrees over a total of 360, and that's reduced down to 1/8. The green is 279 over 360, and when I reduce that, that reduces down to 93 over 120. All right. Okay. One more example. 2 fair dice are thrown. Find the probability that at least one dice is a 6. I'm going to do an area model for this, okay? So we could roll a 1, a 2, a 3, a 4, a 5, and a 6. Or on the second dice, we could do the same thing. Okay. Draw this in here. Now, I'm not going to actually write everything in this time. I'm going to use a little logic so that I don't have to write down so much stuff. It basically told us that one of the dice, at least one, had to be a 6. So all I care about is the columns and rows that have 6 in them. So I'm just going to write these down because these are the ones I care. And then this is a 5, 6, 4, 6, 3, 6, 2, 6, and a 1, 6. Okay, so I count out how many there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the probability of at least 1 6 is equal to 11 over 36. Thank you.